When people hear the phrase, the fifth dimension, they often imagine something mystical or science fiction. But in physics, a dimension has a very specific meaning. A dimension is simply a direction in which movement or measurement is possible. In our everyday experience, we live in 3 dimensions of space: length, width, height. These 3 dimensions are enough to describe where something is located at any moment. But location alone does not describe reality. To fully describe an event, physics requires one more coordinate: time. Time allows us to say not only where something is, but when it is there. This is why time is called the 4th dimension. In modern physics, space and time are not separate things. They are combined into a single structure called spacetime. Every event in the universe has a position in spacetime: 3 spatial coordinates, 1 time coordinate. This framework was formalized by Albert Einstein in his theory of relativity. Relativity showed that space and time can stretch, contract, and curve depending on mass and energy. This means dimensions are not abstract ideas. They are physical properties of the universe itself. So, when physicists talk about a 5th dimension, they are not talking about fantasy. They are asking a serious question. Is space-time complete with only 4 dimensions? Or could there be more? To understand why this question exists, we need to look at a problem that physics has been trying to solve for over a century: the problem of unification. Gravity behaves differently from the other fundamental forces. Electromagnetism, the strong nuclear force, the weak nuclear force. These 3 forces can be described using quantum mechanics. Gravity cannot. This mismatch has led scientists to explore deeper structures of space-time. And this is where the idea of a 5th dimension first appears. In the early 20th century, physics faced a major challenge. 2 powerful theories existed: general relativity described gravity and the structure of space-time. Quantum mechanics described electromagnetism and the behavior of particles. Both theories worked extremely well, but they did not fit together. Physicists wanted a single framework that could describe all forces at once. In 19, a mathematician named Theodore Kaluza made a bold proposal. He suggested that space-time might have more than 4 dimensions. Specifically, he proposed a 5th dimension. This extra dimension was not meant to be seen. It was meant to exist mathematically. When Kaluza extended Einstein's equations into 5 dimensions, something remarkable happened. Gravity and electromagnetism emerged from the same equations. They appeared as different aspects of a single higher dimensional geometry. A few years later, physicist Oscar Klein expanded on this idea. Klein proposed that the 5th dimension was compact. This means it was curled up into an extremely small size, so small that it would be impossible to detect directly. Imagine a long, thin wire. From far away, it looks one-dimensional, but up close, you can see that it has a circular dimension around its surface. Klein suggested the 5th dimension works the same way. Large-scale physics appears 4-dimensional, but at very small scales, an extra dimension exists. This idea became known as Kaluza-Klein theory. It was the first serious scientific proposal that extra dimensions could exist without contradicting observation. Although the theory was incomplete, it introduced a powerful concept. Forces may arise from the geometry of higher dimensions. This idea would shape physics for decades to come. However, Kaluza-Klein theory had limitations. It did not include the strong or weak forces, and it could not fully explain quantum behavior. But it opened a door physics has never closed. One of the most important questions about the fifth dimension is this: if it exists, why don't we see it? The answer lies in scale. Human perception evolved to navigate a world measured in meters and seconds. We cannot see atoms directly. We cannot see space-time curvature. And if extra dimensions exist, they would be far smaller than anything we can detect. Most modern theories propose that extra dimensions are compactified at the Planck length. This length is incredibly small, about 10 to the minus 35 meters. At this scale, quantum fluctuations dominate. Space itself becomes unstable. Direct observation becomes impossible with current technology. This means the fifth dimension, if real, would not be a place you could travel to. It would not be another direction you could point toward. It would be a hidden structure, embedded in space-time. Its effects would be indirect, felt through equations, symmetries, and physical constants. This is similar to how we infer the existence of dark matter. We do not see it directly. We see its influence. In the late 20th century, string theory emerged as a candidate for unifying physics. String theory proposes that fundamental particles are not points. They are tiny vibrating strings. Each vibration mode corresponds to a different particle. But string theory has a requirement. It does not work in 4 dimensions. For the mathematics to remain consistent, string theory requires extra dimensions. In most versions, the universe has 10 or 11 dimensions. This means the fifth dimension is only the beginning. In string theory, extra dimensions are compactified into complex geometric shapes called Calabi-Yau manifolds. The shape of these dimensions determines the properties of particles and forces. Different shapes lead to different physical laws. This idea explains why the constants of nature have the values they do. They may be determined by the geometry of hidden dimensions. The fifth dimension, in this context, is part of a deeper structure that governs reality at its most fundamental level. However, string theory remains unproven. It is mathematically elegant, but difficult to test experimentally. Still, it provides one of the most detailed frameworks for understanding extra dimensions. Another idea involving the fifth dimension comes from brain cosmology. In this framework, our universe exists on a 4-dimensional surface called a brain. This brain is embedded in a higher dimensional space called the bulk. The fifth dimension exists in the bulk. According to this idea, all known particles and forces except gravity are confined to the brain. Gravity can leak into the extra dimension. This could explain why gravity is so weak compared to other forces. If gravity spreads out into higher dimensions, it would appear weaker in our 4-dimensional world. Some models predict small deviations from Newton's law of gravity at very short distances. Experiments have tested this. So far, no deviations have been observed, but the idea remains viable. Brain models also offer explanations for cosmic expansion and the structure of the universe. Again, the fifth dimension is not a place. It is a mathematical extension that helps resolve physical puzzles. One of the most common questions about the fifth dimension is this: does it mean multiple timelines exist? In popular explanations, the fifth dimension is sometimes described as a collection of all possible histories. This idea comes from a simplified interpretation of higher dimensional models. In physics, this interpretation is not literal. Timelines are not considered physical dimensions in the same way space and time are. Instead, they are mathematical possibilities. When physicists use higher dimensions to describe multiple outcomes, They are working in abstract spaces called configuration spaces or phase spaces. These are not places you could travel to. They are tools used to describe complex systems. The fifth dimension in real physics is not a branching path of choices. It is an extension of space-time geometry. Some interpretations of quantum mechanics, such as the many worlds interpretation, do involve multiple outcomes. But these are not extra spatial dimensions. They are different solutions to the same quantum equations. This distinction is important. Extra dimensions are about the structure of space-time itself. Multiple outcomes are about how probability behaves in quantum systems. They are often confused, but they are not the same thing. Not all dimensions are physical. Some exist only in mathematics. For example, a vector space can have any number of dimensions. These dimensions describe independent variables, not physical directions. In physics, dimensions are only physical if they correspond to measurable properties of space-time. The fifth dimension, proposed in theories, is a physical dimension, only in a limited sense. It affects equations, forces, and symmetries, but it does not allow motion in the way spatial dimensions do. This means extra dimensions can be real without being accessible. They can shape reality without being experienced. This is not unusual in physics. Fields, wave functions, and space-time curvature are all real, yet invisible. Physics does not require direct perception. It requires predictive power. Even though extra dimensions are difficult to observe, they are not untestable. Physicists look for indirect evidence. One method involves high-energy particle collisions. If extra dimensions exist, energy could leak into them. This would appear as missing energy in detectors. Large particle accelerators, such as the Large Hadron Collider, have searched for this effect. So far, no clear evidence has been found. Another method involves gravity. If gravity spreads into extra dimensions, its behavior should change. At very small distances, experiments have tested gravity down to fractions of a millimeter. Again, no deviations have been detected. Cosmology also provides tests. Extra dimensions could affect the expansion of the universe, cosmic background radiation, or the behavior of black holes. Observations so far are consistent with 4 dimensions. This does not rule out the 5th dimension. It only constrains its properties. Despite the lack of evidence, physicists continue to study extra dimensions for a reason. The mathematics works. Higher dimensional models naturally unify forces. They explain symmetries that otherwise seem arbitrary. They provide frameworks where gravity and quantum mechanics can coexist. Without extra dimensions, many unification attempts fail. With them, the equations simplify. This does not mean extra dimensions must exist, but it means they are worth investigating. Physics advances by following mathematics where it leads, then testing the results. It is important to clarify what the 5th dimension is not. It is not a parallel universe. It is not a spiritual realm. It is not a shortcut through space. It does not allow time travel. It does not explain consciousness. These ideas appear in fiction, not science. The 5th dimension is a proposal about space-time structure. Nothing more, nothing less. Its purpose is explanatory. If it exists quietly, hidden, mathematical. As of today, there is no experimental evidence for a 5th dimension. There is also no evidence that rules it out completely. This places the idea in a category called theoretical physics. It is a serious proposal but not an established fact. Physicists remain cautious. They separate what is known from what is possible. What is known? Space-time behaves as four-dimensional, at observable scales. What is possible? Additional dimensions may exist, at scales beyond current detection. Science is comfortable with uncertainty. It does not rush conclusions. Even if the fifth dimension turns out not to exist, its study has value. It has led to new mathematics, new insights into gravity, new ways of thinking about space-time. Many discoveries in physics began as ideas that were later discarded, but the tools they created remained. The fifth dimension represents curiosity. At the deepest level, a willingness to question the structure of reality itself.